Hi guys. So today we will be doing chapter 4. I want you guys to have your textbooks along with you as we are going through this lesson. Okay, I'm only going to be able to draw things over here, and if I ask you to refer to something on your textbooks, you should be able to do that. So open your textbooks, or you can open the online version and get it up to chapter 4. All right. um, okay, so just before continuing this chapter, let me just give you some announcements. So you're going to have to submit your homework and lab files online this week. You're going to have to submit them online this week. It For the Monday students, it's going to be due on Monday at 10 o'clock. And for the Tuesday students, as usual, it's going to be due at on the 21st at 10 o'clock, right? So that is for homework and for lab. Homework file, um, uh, yeah, I probably would submit the homework file. I'll upload the homework file on Wednesday or Thursday. So in case you're seeing this video before Thursday, if I haven't uploaded the homework file, I'll most likely upload it by Thursday. So the homework file should be under week 5. Under week 5 in modules, you should be able to see the homework file, and the lab Dropbox also will be under week 5, right? The lab Dropbox, you have to upload two files. One will be the Excel file which we did in the lab class, and the other one will be a Word document which you have to just answer the question which I give you, and your lab grade will be dependent on that. Now, of course, I will not grade the lab based on the error percentage that you got for Excel file. I'll just give it. That is not really relevant. You should show that you have done the lab in that Excel file, and the most of the grading will be done just based on that question which I'm going to give you on the Word document for lab. Okay, and as for homework, it is going to be based on a little bit of chapter 4 and a little bit of chapter 3, like what we covered in the previous week. That is going to be on the homework, right? And the quiz will be the same format. It is going to be on Wednesday for the Wednesday students, and on Thursday for the Thursday students. It is going to have one question from the homeworks. One question from the solved problems which I will be giving, and one conceptual question or two. Okay, so let's. I guess that's it. So let's continue on with the chapter. In case you have any doubts, by the way, this time I'm not going to be having my office hours on Monday and Tuesday, because I'm not. I'm not going to be here. But we can have the office hours on Wednesday and Thursday if you guys need it. So if you guys want to ask me some questions on Wednesday or Thursday, then we can set up a time. Send me a mail, and we can set up a time, and we can meet during that time. I'm not going to be here if no one sends me a mail for me to stay here, right? So on Wednesday and Thursday, I'm going to be here for the lab and the lecture class. But for office hours, I'm not going to have any specific office hours. But if anyone wants to meet me on those days, you can set up a time, and we can try to meet at that time. Okay, let's continue on with Newton's laws of motion, and with what we talked about in the previous class. Let's continue that on to this class. Okay, so in the previous classes, we talked about Newton's first law of motion. We talked about Newton's second law of motion. Um, so Newton's first law, what was it? An object at rest continues to stay at rest, or an object in motion continues to move with the same velocity at constant velocity as long as there is no external force on that object, right? Unless an external force acts on it. So if there is no external force acting on it, it's going to keep going with that constant velocity forever, right? Only if it gets stopped, that's an external force. If there is friction, that's an external force, right? All these other factors are external forces. So as long as those are not there, or as long as the net external force is actually zero, then the object will continue to keep moving, because there is no force. If there is no force, no acceleration. If there's no acceleration, then the velocity does not change, right? Acceleration is the only reason why velocity changes. Okay, so we talked about I mean, I want to change the wording of this Newton's first law a little bit, right? So it says unless there is an external force acting on it, right? So as long as there is no external force acting on it, the velocity does not change. That is what it is saying, right? But there can be there can be situations in which there are external forces acting on an object, but still the object can just remain at rest, or like, just remain, like, at in constant motion. So let's take an example for that. Imagine a table and there is a box on the table, right? There's a box on this table, and if we draw the free body diagram of this box, okay, let's give this box a mass of m. There are two forces acting. The first one, mg, that's the one I would write first, and then there's another force straight up, the normal force, right? Now, how to recognize if there's a normal force acting on an object? If this object is touching this surface, then there is some force between them. We are going to call that as the normal force, right? These are the two forces acting on this object. There is nothing else. The object is not moving anywhere. It's just sitting there, right? Now, in this case as well, Newton's first law applies, because there are two external forces, right? One is this, one is this. Both of these are external forces acting on that object. However, these forces cancel out exactly. Just because these forces cancel out exactly, you can still say that the object remains at rest. So the change in wording that I would do is that an object at rest remains at rest, or an object in motion remains in motion with constant velocity, as long as the net external force is zero, right? That's a much better way to phrase it. Net external force is zero. If net external force is zero, then acceleration will be zero. Okay, so here acceleration only depends on the net external force. Okay, acceleration of any object, it depends on the net force, or the net external force on that object. Okay, what we mean by net force or the net external force is that we have to sum up all the forces. That is the net force, or the resultant force. We did that in the forces lab, right? The resultant force, or the net force, is going to be the sum of all the forces. Of course, because force is a vector, we have to imagine everything in terms of x-axis and in terms of y-axis separately. Now, because this is like, it is vertical, let's call this as the y-axis. Let's imagine a horizontal line here, call it the x-axis. Okay, we have y-axis, we have x-axis. Now, for y-axis, there are two forces acting in the y direction, right? So the two forces are this and this. In the x-axis, there are no forces acting, right? So if you have to write Newton's second law for the y-axis, how would that look? It would be, you have to sum up all the forces, n minus mg. Now I will keep doing this without mentioning the reason each and every time, because I want you to be able to comfortably understand what I mean by adding up vectors, right? If vectors are in the opposite direction this way, adding means subtraction, right? Over here we have a vector up, we have another vector down. So if I want to add them, I can take up direction as positive. It was going to be n minus mg. That is the sum of these two vectors, or addition. Okay, so these are the only two vectors and we've added them. So this should be equal to the net force, right? This should be equal to the net force. This when we say net force, we just mean we want to add the vectors, right? So every time we don't need to write net force is equal to mass times acceleration. We don't need to write that. What we can directly do is in any question, we directly find the net force this way. Okay. In that case, let's even erase this part. Okay. Right. That itself is the net force. Done. Okay. Net force is equal to mass times acceleration. Mass times acceleration. That's it. Right, but remember this is the acceleration in the y direction. Okay, because this is the net force in the y direction, right? This is the sum of forces in the y direction, so this is the acceleration in the y direction. Okay, so this is a valid equation over here. Okay, in this case of the box just sitting there, we can look at that example and we can tell that this acceleration has to be 0. And of course, when you multiply with mass, it's going to be 0, right? So this n minus mg, it is going to be 0. All right. So if you so n minus mg is 0. From that we can say that you can add mg on both sides. That will give you n is equal to mg, right? Now do not remember this as a formula, guys. Again, I don't want you guys to be remembering these things as formula. The only formula thing over here is this. This is the only true formula thing over here. Net force is equal to mass times acceleration. Okay, this is something which we got for this specific example of this object just sitting there, right? So n is equal to mg for this object when it is sitting right there. Right? It's not doing anything. So basically what this means is that, let's try to understand what that means. This object is right here, and yeah, so this object is applying a force. Sorry. The Earth is applying a force on this object, right? And that force is mg, right? And then the object is applying some force on this table, right? You can understand that the object is applying some force on the table. We don't know how much that is. Now you can assume that that is mg. Okay, that is the same force. So basically this object is applying its weight on the table. I don't like this way of thinking because it is not always true. I want to be able to use things which will give me I want to be able to use equations or strategy, I mean, like, the procedure which will give me the correct answer every time, right? So for now, let's just say that this object is sitting on this table, and it is applying its weight on this table. Okay, that is something which you can understand, right? But as I said, that is not the force which that object is applying on that table, right? It is applying some force. Okay, so this actually brings us to Newton's third law. Newton's third law of motion, as I said in class, every action has an equal and opposite reaction, right? That is the simplistic view of Newton's third law, but we have a little more comprehensive formulation of this Newton's third law in the textbook. You can see that in what is this, page number 153. Page number 153, you can see the Newton's third law of motion. You can see the statement given over there. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. Okay, so basically what this is telling is that now we, okay, I want to use the same example, this table example, to describe this Newton's third law. Right. So let's look at the force. Yeah. So let's we've all seen the free body diagram over here, right? We drew one force downwards, that was mg, and one force upwards, that is normal force, and we said that normal force is the thing which this table is applying on this. The normal force is the force which the table is applying on that box, right? On that on this box, this table is applying some force on that box. We are calling that as the normal force. Okay, so what this Newton's third law is actually telling us is that the force which the table is applying on this box is exactly equal to the force which the box is applying on the table. Okay, so the force which the table is applying on the box is equal to the force which the box is applying on that table, and also opposite in direction. It is going to be downwards. The table is applying a force on that box upwards. The box is applying a force on that table downwards, right? And we called the force which the table is applying on the box as N, right? We use this N, normal force, we call that. And I told you that the box is applying some force on the table. I said that the wrong way to word it would be that the box is applying its weight on the table. That's the wrong way of phrasing it. Also, because it might not always be true, right? But I told you that there is some force which the box is applying on that table, but Newton's third law is telling us that whatever that force is, it has to exactly equal this normal force. It has to exactly equal this normal force. All right, so we can just call that as the normal force which the box applies on the table as well, right? So what we generally say, so because of Newton's third law, this actually works in every pair of forces. I will give you some more examples, but because of this Newton's third law, what we actually say whenever we are describing these type of forces is that we say that there is some force between the box and the table. That's it. We don't say that the box applies a force on the table or the table applies a force on the box. The best way to phrase it is that there's some force between the box and the table, normal force. Okay. The same way, I also mentioned another example in class about the gravitational force which the earth applies on you, right? The gravitational force that earth applies on any object, okay, if the mass of that object is m, the gravitational force applied would be m times g. That's it. You just multiply it with 9.81 meters per second squared if your mass is in kilograms, and that will give you the force in newtons. Okay, so that force, that is a force which the earth applies on you, right? However, I told you that the force which you are applying on earth is also exactly the same. And I don't mean that the force which you are applying on the floor below you. I don't mean that. I mean the force which you are applying on the earth as an entity. So even if you're, as I took a silly example in class, remember? I told you, like, if you jump off the building, right? And I told you not to do that specifically. If you jump off a building and you are falling, you're free fall, right? You're in free fall. Remember free fall? So when you jump off a building and you're in free fall, the earth applies a force on you, and that is mg, whether you're in free fall or whether you're on Earth, as in whether you're still on Earth, it doesn't matter. Mg is the force which the Earth applies on you. But you see, even as you're falling down, you are applying a force on the Earth, and that is exactly equal to this mg. So if the force which the Earth applies on you is 700 newtons, then regardless of whether you're falling down or you're just standing on the ground or whatever you're doing, if you're just going in an aeroplane, doesn't matter what you're doing, the force which you are applying on Earth is the same 700 newtons force. That is not because you're touching the ground, right? The force which you are applying on the ground, that is the floor or whatever, that is the normal force, right? Because normal force is the contact force. It requires a touch. However, gravity, it does not require a touch. It is long distance as well, right? The Earth's gravity on any object which is in the vicinity of the Earth, let's just say, like even airplanes, although they are going away from the Earth, they are going at a high altitude, it's still in the vicinity of the Earth, because like if you imagine the Earth as an apple, the Earth's atmosphere is so thin, it's approximately like the skin of the apple, that's it. So not much. So the Earth, everything around, you go in a flight or anything, you're still in the vicinity of the Earth. The Earth's applying almost the same amount of force on you, mass times g, right? Now, of course, technically speaking, the amount of force, even if you're flying, if you're flying on a flight, is slightly lesser, but it is so less that it doesn't really matter. At least for this course, we are not going to take into account what the difference in gravity is when you're going at a higher altitude or so is. Okay, so let's come back to this. So the Earth is applying a force on you, and you are applying the same amount of force on Earth, right? So that's an action reaction pair, we can say. Okay, over here as well, the action reaction pair, you can write the action as this, that the table is applying a force on this object. The reaction is that the object is applying a force on the table. Okay, both of them are exactly equal, and we will call that as the normal force. Okay, so as I said, we want to be able to refer to forces always as forces between objects. So normal force is the force between this table and this box, right? And then as for gravity, you can say the force of gravity between you and the Earth is whatever, the 700 newtons or so. Okay, in that is a better way of saying it, rather than saying that the Earth is applying some force on you, because you are also applying the same amount of force on Earth, right? Now, it is not true that these forces cancel. Like I drew a force up, I drew a force down. I say that these both are exactly equal, and they are opposite to each other like this. Why should they not cancel and nothing? Why is it not the case that it just cancels? That's a good question to ask if you had that doubt. It's a very good question to ask, because these are forces, these are vectors, obviously. Opposite and equal should cancel out, right? However, when we draw free body diagrams, the main important thing is this. This comes to one of the most important things in free body diagrams, is that you are only supposed to draw the forces acting on the object, not the forces which the object is applying to its surroundings. Okay, so so that is the reason why in our free body diagram I did not draw n like this and another n like this. I just drew one n this way because this is the force which the table is applying on that box, right? But in reality, what happens? the table applies a force on the box and the box applies a force on the table. That is how it actually happens. However, I just drew the part which is the table applying the force on the box. Hey, this color seems interesting. Oh, there are some stars over here. That's cool. That's cool. Never mind. Okay. Um, so this is one force, and the second force on this object is mg. This is how we have drawn free body diagrams, right? Again, I am not drawing the force which this object is applying on the earth. I only want external forces. External forces are forces which other things are applying on that object. Okay, so first we have to select an object which we are interested in, and then figure things out. Okay, so we selected this object, and then we are drawing the forces on that object. Okay, these are the only two forces on that object. What we mean by on the object is the force which is being applied to that object. Like, this table is applying a force on that object, and the earth is applying a force on this object. So I drew out those two objects. Knowing what all forces to include in the free body diagram is tremendously important, guys. And of course, solving the free body diagram, splitting vectors into components, writing this equation f equals ma, all these things, all of them are important. But the first and foremost step is recognizing forces, right? So let's see. So first of all, in your textbooks, if you see free body diagrams, the way they have drawn it is slightly different. Instead of drawing the object, they just drew a point like this, and then they drew an axis like x and y axis, and then they drew the forces, like, one force this way, the other force that way. They just drew that. Okay, so I mean, this is not wrong, obviously, and in a lot of textbooks I've seen people, I mean, I've seen them do like this. um, but actually, I mean, actually, I don't like this for a few reasons, or I don't have any problem against this. But I think that, like, drawing a free body diagram with the actual object shape is much better. Or even if you don't draw the actual object shape, actually the best thing I would say is to draw a rectangle. Always draw a rectangle for any object. That is the recommended thing that I would tell you to do. There are many ways, many reasons why this is going to be more important than just drawing, I mean, more easy to understand, or so, than drawing a point. Okay, so first of all, it gives you an orientation for this object. If the object is oriented this way, right, a point is not going to tell you whether it is oriented this way or if it is oriented this way, right? If it is oriented this way or this way, a point is not going to tell you that. So I think, like, that is one use, and there are other uses as well, which we will come to later. So when I'm talking about free body diagrams and all, I will be using a rectangle for my object. Okay, no matter what object it is. If it's a person, I will still draw a rectangle, right? Okay, let me see if I can clear some of this out. So what is this? Let's see. Okay, I guess I have to just clear everything this way. Okay, I hope that there was a clear all button, but I don't find it. Okay, so we will look at some scenarios and we will try to figure out what the free body diagram for each of these is. Okay. So we talked about one example in class of the that is the example which we did in the lab class as well. The lab class, we looked at a cart and uh, a pulley over here, and there was a hanging mass over here, right? That was the example that we looked at, and then we figured out what the acceleration should be. If you know the masses, if you know the mass m1 m2, we figured out the acceleration, right? So that is one scenario. Okay. For that, of course, free body diagrams were important, but also we will talk about some other scenarios. I'm trying to look at the textbook to see if I can find some. Okay, so I will actually take this example. So in the textbook, this is page number 159. Page number 159. So this is a two-dimensional problem. Okay, so weight on an incline. So let's see. Let's erase all of this. I will draw the scenario over here. Okay, this requires multiple things from us. All right, it requires us to actually split the forces into components and stuff. Okay, so let's do this example. So let's say that they've given this is an inclined plane. So an inclined plane is something which is inclined at an angle, right? So if you have an object over here, it is going to go this way, right? It is going at an angle like this. It's an inclined plane. We did this in the first lab, if you remember. Okay, it's inclined at a specific angle. It's given to us. The angle is given to us, and for now, just for now, ignore the friction. Let's say that the friction is 0, right? It's maybe ice or something, so that the friction is roughly 0. Oh, okay. Okay, the friction is roughly 0. So we are going to imagine that this person is on the skateboard. As I said, I will just draw the person as a box just so that I don't unnecessarily waste time in drawing the shape of the person or anything. Even if you draw the person over here, especially when you draw a free body diagram for this object, I would always suggest you to draw just a box instead of the person. So you can already see that just by drawing the shape in this particular direction, it is giving a sense of the orientation, right? It's giving you an orientation for this object. Okay, so let's try to frame a question. Friction is 0. Okay. Yeah. Let's just say find the acceleration of this person. Okay, I need to give the mass, obviously. Mass of this person is, let's say, 70 kilograms. Okay, 70 kilograms. I am not giving anything else over here. I'm gonna ask you to find the acceleration of this object as it is going down, and it's starting from rest. So initial velocity is 0. Right, initial velocity is 0, starting from rest. What is the acceleration of this object? Okay, so to be able to find the acceleration, we need to know the net force. If we know the net force, we can find acceleration, right? And one important thing to notice over here is that the object would only go in this direction, right? It would not jump up or down this way. It would only go in this direction. But that's a problem because this is neither horizontal nor vertical. So can you say that this is in the x direction or in the y direction? It can get a little complicated if you do it that way. I mean, you cannot really define this as any one direction. So what you can actually do, you could actually just go with the x x-axis and y-axis this way. Oh, this was big. Let's take a small one. Right, you can actually draw the x-axis this way, y-axis this way, and do everything this way, but a better thing to do would be to draw the x-axis this way. I'm gonna call this as the x-axis and this as the y-axis, right? Let me just draw that a little better. Okay, that is my y-axis and this is my x-axis, right? Now the object is going left, so it is in the negative x-axis, right? Okay, and the up direction is just up, just y. Okay, it is not exactly up, but it is diagonally up. Whatever, you cannot take x-axis this way and then y-axis this way. You cannot do that. Both have to be perpendicular to each other, right? Both have to be at 90 degrees with each other. Okay, so the reason why I took it this way is because this acceleration, the object is going this way, right? So acceleration is in only in the x direction. The acceleration in the y direction is going to be 0 because the object is not the object is not jumping up or down this way. It's not going in the y direction, so I specifically chose this so that I can say that the acceleration in the y direction is 0 and acceleration in the x direction is just the acceleration of this object. We want to find this, so let's put double question mark for this. Okay, so first step is to draw the object all by itself this way, right here like that, and then to recognize the forces acting on this object. Okay, to recognize the forces acting on this object, let's first get our x and y axis also over here. X-axis, y-axis. Okay, let's recognize the forces acting on this object. One force would be the force of gravity. By the way, whenever you're drawing forces, just draw from the center like that. And this would be mg, or you can call that as weight, w. It's fine. I prefer mg. Okay, mg as in like, you know, this 70 multiplied with 9.8, whatever, all of that. Okay, so the thing to notice over here is that I'm not drawing the force of gravity this way. I'm drawing it exactly vertically downwards. Why? The force of gravity is just vertically downwards. That's it. There's not even if the object is oriented in a different direction, if it is going in a different direction, doesn't matter. The weight of the object or the force of gravity is just mg downwards. Okay. Are there any other forces acting on this object? To recognize whether there are any other forces acting on this object, what you have to do is you have to see what the object is touching. The object is not touched by any rope, right? There isn't any rope attached to that object, so no tension force. Gravity mg, we've drawn that. But the other thing which the object is actually touching is right here, right? So that is the normal force. There will be a normal force because of that touch, and normal force is always perpendicular to the surface, right? It is perpendicular to the surface. We can write that as n. These are the only two forces acting on this object because it is not touching anything else. Okay, normal force is already in the y-axis. It's already, you don't need to split it into any components because you need to get everything into the x components, into the x directions or y directions. Normal force, it's already in the y direction, so the x component of normal force is 0, y component is just n, right? So I mean, you can write this, but like, you know, this is not extremely necessary. If you start drawing everything in terms of free body diagrams, you will see that it is much easier to just directly draw that. Okay, however, this mg has to be split into components, and you can already see it is this way, right? So it has to be split into this side and this side. You can already see that those are the two directions in which it has to be split. Okay, to be able to split that into the components, you need the correct angle. And what is the correct angle? Correct angle has to start from the positive x-axis and then go towards the vector. As it is going towards the vector, it has to be counterclockwise direction. So that is the correct angle, right? So it has to start from here, and you cannot take the easier route because this is clockwise. You have to actually go all the way, and this is the correct angle, right? So you need to somehow figure out this correct angle, right? you, for that for that purpose, I will tell you, go back to the original picture. Okay, do not write the forces over here itself. I don't want you guys to be saying n mg and all those things over here. Sorry, this is not mg. Like, n and then mg and all those things over here, right? That you have to mention that in the free body diagram, right? Here, right? That is the place for recognizing all the forces. To solve some geometry issues, you come back to the original picture, and now you want what? You want the correct angle. So how do you find that correct angle? You need something. So you need to find this entire thing. So maybe if you find this small thing, you just add 90 to or let's not go in that route. You need to find this entire thing, but from here to here it is 180. If you are able to find this one, then you're done, right? You add this to 180, you'll get your answer. Okay, so for that, as I said, let's go back to our picture over here. Picture over here, and let's draw a line straight down. This is for that gravity thing, right? Straight down. If we can find this angle, then you just take this angle and then add 180 to it. That'll give you the total correct angle, right? So it now you can already see that you look at this triangle, you can find that angle because this is exactly vertically down, this is exactly horizontal. So this is a nice triangle. Over here this is 25 degrees, right? And right angle triangle, horizontal, vertical, so it has to be 90 degrees. Okay, so if this is 75, if this is 25, this has to be 65 degrees. This has to be 65 degrees. So we were able to successfully find that this angle is 65 degrees. You add 180 to it, your total angle will now be, what will it be? 180 plus 60, so that will be 245 degrees. 245 degrees, that is the total angle. Now you can split your mg into components, right? So you can say weight x and weight y. So w for weight, by the way, w for weight, and weight is just mg. Okay, weight stands for mg, and you can find the x component of weight and y component of weight by doing just the mg times cosine 245 degrees, mg times sine 245 degrees. Okay, m is given to be 70, g and then 245. Let me just quickly do that in the calculator and see what I get. Cosine 245 degrees. I have a negative value, which absolutely makes sense. And then I have to multiply this with 9.81 times 70. Okay, so I have a value over here of negative 290.81 2 2. Okay, don't forget the unit for weight is also newtons, because weight is the gravitational force on an object, right? So weight is a force, so it has to be units of newtons. Let's do the same for this. Sine 245 degrees, again I get a negative value, which makes sense, times 70 times 9.801, negative 622.36 newtons I have. Okay, I was able to split these into components. Now what I'm going to do is this. I'm going to draw out the components over here, right? This and this. Okay, the x component is 290.22 newtons. Sorry, this is the y component, right? 622.36 newtons, that is the y component. And x component is 290.22 newtons. And now you should observe here that I did not mention the negatives over here. If I mention the direction, I've already mentioned that this is downwards, right? So I don't need to mention the negative. All right. If I mention down and if I mention the negative, I'm going to get a wrong answer. Okay, so the negative sign is only telling you that it is downwards. So I was able to guess just by looking at the picture. Wait, what am I doing? Okay, yeah. So just by looking at this vector, mg vector, I know that it has to be left and down, right? So I've drawn those arrows just by guessing it, and then my values are just this. I just wrote down the values. Okay, that is the next step, right? So I'm going to erase this for now, all the components, how to figure out the components thing, and we want to find the acceleration, right? And that is the same as the acceleration in the x direction. Okay, so we now actually, as soon as you split this vector into components, right, you can completely ignore this vector. You can completely ignore this in your equations. This should not come up. Now you only have three things. One is this down here, one is this to the left, and the other one is this. All right, so in the y direction there are two forces, N and this one, right? These are the two forces in the y direction. And in the x direction there is one force, only one force, and that is this. That's it, the only force in the x direction. We know that the acceleration in the y direction should be 0. Let's write that equation right now. So n minus 622.36 should be 0, because acceleration in the y direction is 0. So sum of forces should be 0. Okay, so from this you can actually find the value of n as well. It is going to be, if you add 622.36 on both sides, you're going to get, that's it. And then let's find the acceleration. For that you need to write the equation in the x direction. Let's do that. Equation in the x direction. So first of all, the force is to the left, so negative. You can take the left direction as positive, and it'll be fine. You can take the left direction as negative, it will be fine. Just for now, I'm going to take the left direction as negative, and let's see what we get. Okay, so negative 290.22 newtons, that is the total force in the x direction. There are no other forces counteracting it or anything, right? The only force in the x direction is this. So I wrote that force down, because net force in the x direction should be mass times acceleration in the x direction. So it should be just this. So this will actually give you a negative value for acceleration. Negative 290.22 divide with 70. If you actually work this out and see what you get, let's see, 290.22 divide with 70. Okay, I have an acceleration value of negative 414, negative 4.146. Don't forget meters per second squared. Okay, so because you have a negative value for acceleration, your object is actually going to the left. Okay, so this is what happens. Like if you take the right direction as positive, you'll get a negative value for acceleration, which is indicating the direction. Now if you take the left direction as positive, you'll get a positive value for acceleration, just telling you that yes, it is in the positive direction, and positive direction is to the left, so yes, acceleration is also to the left. In both cases, it is giving you a value for acceleration, which is 4.146 meters per second squared, and it is giving you a direction. It is giving you that the direction is supposed to be to the left. Okay, so that is how you can solve this question. Okay, now let's try to understand this. First of all, I want to clarify one thing. You see the normal force over here, normal N. We use the symbol for normal force N. We use the symbol, right? We also use the same symbol N for newtons as well. That's the unit, right? This is actually equal to kg meter per second squared. Remember? This is a unit. We use the unit. We use N for the unit. We use N for the symbol for normal force as well. Okay, so I mean, don't think that you're multiplying 622 point something with the normal force. This is not multiplication with normal force. This is just the unit. Okay, so this is a very good example. It's a very important for you to understand this example to be able to solve these type of questions. You might have to split vectors into components and write equations in the x direction and in the y direction separately, this way. All right, so this is an important part of this chapter. So in the coming chapters, we are also going to be looking at frictional force. But before going to that part, I do want to talk about another example. This actually involves tension in the tightrope. Okay, so tension or rope type of examples, it can be done in multiple. I mean, you can have like different types of examples for those. But the one I'm talking about is page number 163. Page number 163 in your textbooks. You can see that a tightrope walker, he causes a wire to sag by 5 degrees. Let's see what is asked in the question. What is the tension in the tightrope? They're asking you what is the tension. Okay, so let's try to do that. I'm gonna erase all of this, and we can. I'm surprised that there is no erase all option, but okay. So let's do that manually. Okay, so let's try to draw out the scenario. There's a rope over here, a rod over here and over here, and there's a tight rope attached to this rod, but this person is standing on the rope, which I did not draw out well. let me go back. And yeah, this person is trying to balance on that rope, right? Okay, so the angle over here is given to be 5 degrees, so that's good. 5 degrees, maybe I drew it a little more than 5 degrees, a lot more. But we want to find the tension in the rope, like, you know, tension, we want to find that tension. Okay, to be able to solve these type of questions, what we want to do is to draw out the free body diagram for this person, right? The free body diagram for this person. Actually, more accurately, we are not drawing the free body diagram for this person. We are drawing the free body diagram for the center of the rope. Okay, free body diagram for the center of that rope. I just drew a dot over there for that. Let's have our xy. Before having our xy axis, we need to recognize the forces, right? First, let's go and do that. Okay, so the person is applying some force on this object, on this rope. Okay, again, if you use the same trick as what we've done before, we can find that that force is equal to normal. That is the normal force, and that force is exactly equal to the weight of this person. Now we cannot assume that that's the case all the time, guys. Normal force is equal to weight of the person. Not always true. It's only true if that person is not it's not if that person is not if there are no other forces being applied on that person except that normal force and gravity. So if there is an extra normal force, then it's not true, right? If there's a rope pulling that object up, trying to pull it, it's not true, right? So only for this situation, and also for the situation in which this person is just stable over there, he's balanced, he's not going up or down in that case. Yeah, so I'm just drawing the weight over here, and then we have let's draw that a little flatter than that, almost the same. Okay, fine. Tn, this is the normal force. No, this is the tension force, right? This is the tension force, and this is also the tension force on this side. Tension force. These are the three forces over here. You want to be able to find it. Find the tension force. Okay, the angle is given to be 5 degrees. So let's use this to draw this over here, and this is 5 degrees, 5 degrees. Okay, so let's draw the axis. So there are these two forces are there like this. We have weight this way. I can just take this direction as the y-axis. This is this as the x-axis. You can choose this however we want. Now we want to, again, like, you know, we have tension over here. Do we have the weight of the or the mass of the object of the person? Yes, 70 kilograms. 70 kilograms is the mass. 70 kilograms. So the weight would just be 70 multiplied with 9.81, right? 70 multiplied with 9.81 meters per second squared. Let's see, weight of this person, 70 multiplied with 9.81. So 686.7 newtons. That is the weight of this person. And yeah, so that is this force downwards. Now we do not know the tension force. However, we know something about this angle, right? 5 degrees. We'll try to use that. But to be able to split this force into components, we need the correct angle. So we need this one right here, because that is from the positive x-axis counterclockwise, right? So you can find this angle by knowing this angle, by knowing the 5-degree angle right here. You can find this angle as well. Just because this is 5 degrees, this has to be 85 degrees. And if that is 85 degrees, then this is 85 degrees. This is 5 degrees again. How did I find that this is 85 degrees? Okay, so the way we can find that this is 85 degrees is that we see this triangle right here, this entire one. This angle is 5 degrees. This angle is unknown. We want to find that. But this angle right here is going to be 90 degrees. It is vertical and horizontal, right? So exactly 90 degrees. So 90 plus 5 is 95 degrees. But the sum of angles in a triangle has to be 180 degrees, right? So if this is 95, this has to be 85. Only then it'll work out. So that is how we were able to find that this angle is 85 degrees. And then again, you can find the correct angle by, yeah, we have found that this is 85 degrees, so this has to be 5 degrees because the entire thing is 90. Okay, now what about the other force? For the other force, we want that other angle, right? We want the bigger angle. Yeah, so we want this angle right here. So to be able to find that angle, we know that this is 5 degrees, so this again has to be 85 degrees, right? This should be 85, and the remaining part from here to here, that is just 90 degrees because it's just perpendicular, right? So we have to do 85 degrees plus 90 degrees. That is the true the correct angle. This big one right here, that is the correct angle. So this is 175 degrees. Okay, so now we want to split these vectors into components, the t's. So let's use this. It's already a big mess over here, so I'm going to draw this again. Y-axis and x-axis, y-axis. Just for the components, you can draw a separate picture like this. That is actually highly recommended. If you just want to squeeze everything over there, it's fine. It's totally fine. It's not a big deal. This is one vector w. It only has one component, which is y direction, negative y direction, so downwards. Now this t right here, the t has to be split into two components. One will be to the right and the other one will be upwards, right? You found the correct angles, 5 degrees and 175 degrees. So t times cosine 5 degrees will actually be t times some value, right? You just write down the value over here, and then you have your y component is t times sine 5 degrees. Again, t times some value over here. Okay, so we were able to split this into components. Now what about this? The angle is just 175 degrees, right? So you have to split this into components. You will get a negative value for the x component, and you'll get a positive value for the y component. Okay. Now after you do that, you have to the one thing which you can do is actually let me just solve this a little bit, so that let's see, cosine 5 degrees. Oh, wait. Cosine 5 degrees. Okay, so cosine 5 degrees, I have a value of 0.996. Okay, don't forget it has to be multiplied with t, so I just wrote that over there. Sine 5 degrees is almost going to be 0, so sine 5 degrees. 0.087 in t. Okay, so that is the x component and y component of this force right here. We want to find the x component and y component for this force right here. Let's do that. Tx t cosine 175 degrees. Remember, this is 175 degrees. So what will that be? I'm going to tell you what it's going to be. Once you do it in your calculator, you're actually going to see that it is negative 0.996 t. It's going to be this. And ty is going to be t times sine 175 degrees. And I'm going to tell you what it's going to be. Once you do it in your calculator, it's going to be 0.087 and t. Now what you can notice after looking at this is that the x component of this is exactly opposite to the x component of this. This makes sense because look at where this the vector over here is. It is to the right, up and right, right? Over here it is to the left and up, right? So both the ups combine, but the left and right cancel out. So that is exactly what is happening over here. The x components are canceling out. The y components are getting added on because both of them are equal. Right? They're not equal and opposite. They're not negative and positive. Both are positive. Okay, so when you add the total y forces, if you add up all the y forces, net force in the y direction. So first of all, net force in the x direction, 0, because these are the only two forces. Both of them are cancelling out. Net force in the y direction, you have to do this plus this because they get added up, right? So let me do times 2 and see what I get. 0.174 t. Okay, but don't forget this w, guys. Don't forget this w right here. Okay, this also exists, so this has to be subtracted because these two forces were up, both of them were up, right? So this is down, so it has to be minus w, and w is just 70. So sorry, w is just mass times g, right? So 70 times 9.81 meters per second. So once you find all of this, yeah, now you have this. Okay, so over here the net force has to be 0 over here as well, the y in the y direction. The object, the question would just say that the person is not jumping up or down, he's just stable over there. If it is stable, then this should be equal to 0. From this you can see that the only unknown thing over here is this t. You can find the value of tension by doing this. So let me just quickly do that as well. 70 times 9.8. Uh, 686.7. Okay, I'm adding this on both sides, so this goes away when I add that. Okay. Okay, and over here we have 0 point same thing, t. So to find the value of t, You just have to do, you have to divide this with this number. Okay, so let's divide this with 0.174. Okay, so the value of tension I have right now is 3946.55 newtons. Okay, so that's the process, guys. So even in your textbook, if you actually see what answer you have, let's see what they have as a final answer. Yeah, 3900 newtons is what they have. Now obviously there is some error over here because while using those calculation while doing those calculations, we've taken two decimal places, right? We are three decimal places I've taken, but like there was always some error over there. Like if you increase the number of decimal places you take for calculating these kind of things, you'll get much better answers. Okay, so we are going to just stop right here, guys. We will continue on with this chapter and with the next chapter as well in the next class. All right. So yeah, don't forget to submit your homework and lab, um, and also be prepared for the quiz uh, on Wednesday, and for the Thursday people, it's going to be on Thursday, right?